In this video, we are talking about week 6 from Math 277, where we are covering how to find domains of multivariable functions, as well as talking about how to find level curves using this method, as well as how to find partial derivatives to the first and second order. Okay, so the first thing that I'd like to open up with is how we can use domains when we're talking about multivariable functions. So we want to use domains to find non-permissible regions of functions. So this could include things like, things that we know to be non-real numbers. This could be even square roots of negative numbers. This could be ln of 1, or anything where our denominator is 0. So those are things we want to look out for. And in order to find where in a region our domain is permissible, we use test points to see where our permissible regions are. So this will make a lot more sense when we move on to our next examples. But in this space here, we have a curve that represents this function right here, given here. Right, so that splits our graph into two different regions, region 1 and region 2. And we would use two test points, one in each region, to see if it satisfies the properties of that function where it produces real and defined numbers. Okay, so let's take a look at some illustrated examples. So the very first thing that we're going to do is we're going to find non-permissible values, or I'm going to say conditions. So if we start with our first one, actually no, wait, sorry, second, and then use test points. That's a lie. Hold on. So sketch the non-permissible function. And then use your test points to find which part of the graph you should shade in. Okay, so in our first example, we are given a function of f at x and y equal to x minus y squared plus 2. So this is a 1 over situation, so this means that we don't want to have a 0 in our denominator. Can't equal to 0, right? So we're going to isolate that on its own. And this has to be greater than 0. So use inequalities to define non-permissible values. And if we rearrange, is greater than y squared minus 2. And this looks like a parabola. And we've got a positive y value equal to x. So this is a horizontal parabola. And it opens right. So if we draw this out, Okay, so we're going to have an x-intercept of -2. And because our inequality does not have an equal sign, we are going to represent this with a dotted line. So that leaves these whole regions here. Ooh, that's bad. I wonder if my highlighter will work. Okay, it will not. Okay, but in any case, it splits it into two regions, to the left and to the right of our curve. So we want to test if where our points are true. So we're going to test a left point here and a right point here. So let's call this point, I can do this in a different color actually. This is blue. I'm going to say this is like 8, 0. And this test point is -3, 8. Okay, so given those values, let's test to see if they fit our needs, right? If it's greater, if this whole function is greater than 0. So let's test left. So for our x value, we've got -3 minus 8 squared plus 2. It's -3 minus 64 plus 2. Sorry, I apologize. This inequality is meant to be not equals to 0 because we can still have a negative value. It just can't be 0. So let me change that. Okay, sorry, continuing on. This is not equal to 0. So let's keep going. This is -65, and that is not equal to 0. So this section tracks. We're allowed to use that region. And now if we test our right point, I'm going to plug in for x, y equals not equals to 0. And this gives us 10, which is not equal to 0. So both regions are valid. So because of that, let's now put a test point on our curve. So let's actually do our intersection because we know what that is. That is it's -2, 0. Okay, so on curve, if we plug that in, so x as -2 plus y is equal to 0 plus 2, that gives us 0. And this is false, not false, false. So now we know that our domain, which we represent with DMF, so for our x and y that are real numbers in R2 space, we have x minus y squared plus 2 can't equal to 0. Right, and that is basically our limit. Okay, next example is pretty quick, so even though it may look complicated, I want just to think about some properties of square roots. So negative roots can break negative numbers. Right, so if you had like cubed root of a negative value, it would give you a negative answer. But if you did that with an even one, say to the 2, that would not exist, right? So taking a look at this example, we see that we are given to the power of 7, to root 7. And by that logic, any number can be inside the radical, whether positive, negative, or 0. So because of that, if we drew this out, we would just be shading the entire region of our graph, because we're allowed to use any number at any point, and this would still give us a real value. So our domain is defined by x, y, where all numbers are permissible. So we just stop it there. Okay, in our third example, we are given, see screen. We're given the natural log of x plus y. And we know that the highest number a natural log can be is 1. So ln 1 equals 0. So ln can't be negative. And ln can't have 0. So the largest value, the smallest value we can use is 1, which will give us 0, right? So we want whatever is inside those brackets to equal, to be greater than or equal to 1. So x plus y is greater than or equal to 1. So the part that we isolated for, this x plus y, if we moved it around, would be x equals, actually no, let's do y equals. So if we graphed it, this could look like y equals negative x plus 1. If we just treated this inequality as an equal sign, and that means, I'm going to redefine this inequality. This is a lie. It just can't be 0, because if you did ln of 0.5, that also can work. This just has to be greater than 0. Apologies. Okay. So if we move that around, that gives y equals negative x. So if we were to graph this out, this curve would appear like this. So now we have two regions to look at. We have above our curve and below. Okay, so I want to choose a test point that fits this equation here. So let's use our below the curve first, and let's use test point use -2, 0. Just about right here. So let's plug that into our x plus y greater than 0 inequality. So this is -2 plus y, plus 0 is greater than 0. and this is false. So we're going to reject this. And if we did the same for above our curve, so let's use test point positive 2 and 0. Then this becomes 2 plus 0 greater than 0. And 2 is greater than 0. So this is true. So if we were to redraw this function, we would only be shading in the permissible part. We only shade in above the curve because, as we tested, that is the only place where it fits our conditions. Right? And it's a dotted line because it's an inequality that is just greater than, not equal to. Right? And then we're just going to shade in our top portion. So finally, writing this out, our domain is equal to, need a little more room to write this. So for every x and y in 2 space, x plus y must be greater than 0. Okay, and that is our third example done. Okay, last example here. So now we're kind of working with 2 conditions. So everything under here must remain positive, right? Because this is a square root, so it's an even radical. And everything in here must also be positive, or sorry, greater than 0. So because we have 2 shelled conditions, we're just going to start off using what's inside our ln. So let's start with ln. Because if your ln is not permissible, then your radical won't be. So that's why we're only going to isolate this part. So we're going to start with 17 minus x squared minus y squared. And in our previous example, we know everything in a ln must be greater than 0. Now for graphing this, to rearrange it, this could look like x squared equals negative y squared plus 17. And this is again a parabola that opens left. Okay, so if we were to draw this out, this would look like, so plus 17. Okay, so we have 2 regions again. Okay, I'm going to restart with this one. I think I made a mistake. I'll explain from the start. Sorry, ignore everything that just happened. Okay, this is not a parabola. I repeat, not a parabola. Okay. So, yes, it's true we have to start with this condition here, but we also need to make sure that our ln is positive, right? Under that radical. So, we know that ln 1 equals 0, and anything under 1, anything in between 0 and 1 will be negative, because if you plug in for ln 0.5, for example, you get a negative number of negative 0.693, and we can't have negative numbers under our radical. So in this case, this has to be greater than or equal to 1 this time around. So if we rearrange, this will give us x squared plus y squared. And then let's move that 1 over. Actually, let's move all of it over. Okay. Hold on. Okay, so 16 is greater than plus y squared. I'm just going to flip that around. Okay, so this is another form of this equation, which we can also use. So if we're graphing now, and we move that 16 over, and we divide both sides by that 16, this is an equation of a circle. With a radius of 4 centered at 0 and 0 because we have no hk values. So this becomes, and now we're going to use a solid line because we're using greater than or equal to, and square root of 16 is 4, so we have 4 and negative 4, and it's solid because we have a greater than or equal to inequality. So we have two regions to consider. We have inside our circle and outside. So we're going to do two different test points. We're going to do outside, and let's call this -5, 6, and inside. And let's just use something simple, our origin. So let's test inside to see if it fits our expectations. So we need x squared plus y squared is greater than or equal to 16. Sorry, is less than or equal to 16. So then that is 0 plus 0 less than or equal to 16. And 0 is less than 16. So this is good. So we can use our inside region. Let's test our outside region. And this will give us, so we have -5 squared plus 6 squared, 16. And this gives 25 plus 36, which is definitely bigger than 16. So this is false. So we can't use it. So now that clues us in to where our domain is, and our domain can only be permissible inside the bounds of our circle. So let's write out our domain. So for x and y that are real in two space, x squared plus y squared must be less than or equal to 16. You can write it in this form, or you can write it in this form above. Just make sure you know how to get to both. Okay, so that covers domains. Next, we're going to be talking about level curves. All right, so talking about level curves, some places you may have seen level curves are on topographic maps, as well as forecast maps. So these are used for maybe isobaric or isothermic regions. Isobaric means same pressure, isothermic means same temperature, or for, actually I don't really know the word for topographic maps, but they're basically used to, so they join areas of equal value. So for a topographic map, so say you had a mountain that looked like that, right, from a side profile, and you want to look at it from above, right? You want a bird's eye view of what this looks like. So if you were to draw red lines that go all the way across each point at the same height, and they curve based on the topography or the texture of the slope. If we did a top-down view, this would look like, so the lines are closer together where there's more slope, and further apart where there's less slope. Right, so that's what it could look like for this part of our peak. And this peak is less steep. It's got bigger regions, right? So this is a topographic map example, right? It's basically just a top-down view of a surface, right? Where the concentric lines represent areas of equal height and also show us slope. Right, so we're going to talk about how we can apply our knowledge of math to create level curve graphs. Of course, they're not going to look quite like that, but just pretend you live in a world where they do. So we're given a function, and we want to find what it looks like at these different regions. So these values of c are going to be what's plugged in on our left side of our equation. So if we were to start with our first value of 0, we're going to make it equal to our function. And we're going to move the values around until we see something that we recognize. Let's move that 4 back over. And let's divide by 4. So when equal to 1, these have the same radius. And we have a positive x square value and a negative y square value. And we can recognize this as a hyperbola. Now we want to find out if it opens up and down or left and right. So we can plug in 0 to find our y-intercept. So this is squared equal to 4. Y is equal to positive or negative 4. Right, so we do have a, sorry, give me a second. So this is negative y squared over 4 equals 1. And this is y squared equals negative 4. So this has no solutions, right? So there's going to be no x-intercept in our hyperbola. So that can clue us in to open left and right. Right, so our first one we did in red. And this opens left and right. So this is c equals 0. Okay, we're going to do the same thing for our next variable, which is 4. So we're going to make this equal to 4 now. Right, we've got 4 on both sides. So this is, and this is y squared minus x squared equal to 0. And this is a difference of squares, so we can do y minus x times y plus x. And this gives us y is equal to x, and gives us a second equation of y equals negative x. So we know those look like this. Like that. This is y equals negative x, and y equals positive x. Okay, and our last one is if we plug in 8. So if we plug in 8 on our left side, this gives us 4x squared. And this gives us y squared minus x squared over 4 equals to 1. So it's also a hyperbola. And we want to know which way it opens. So we're going to do the same thing, and we're going to plug, let's plug for our y equal to 0. Right, so that gives negative x squared over 4 equals 1. And this is x squared equals negative 4, which doesn't exist. This has no solutions. So we know that there are no x-intercepts. So that means this must open upwards. And this is our c equals 8. Okay, and that's it for this question. So that's how we can use our knowledge of recognizing different kinds of curves in 2D space to find what level curves look like. Okay, is this different? Oh no, this is the same. Okay, new example. All right, so we're going to do the same thing. I'm going to start with 0 first. So 0 is equal to 4x squared plus 10y squared minus 64 over 12x squared plus 6y squared. When we cross multiply our denominator with our 0, that just also leaves 0. So this is 0 equals 4x plus 10y squared minus 64. Let's move that 64 to the other side. 4x squared plus 10y squared. Let's divide by 64, so this is 1. And 4 over 64 is 1 over 16. So this is x squared over 16 plus 64 divided by 10. This is 32 over 5. All right, and we want to find what this looks like. So we already know that with two different radii and positive x squared and y squared values, this is an ellipse, right? So we're going to do a little bit of math to find where our intercepts are. So let's find our x-intercept. So we're going to set y equals to 0. So this gives x squared over 16. Right, and this makes sense because our radius is going to be 4 on our x-axis. Well, 4 and negative 4. Sorry, let's draw that better. Right, so there's our first intercept. If we do our y-intercept, we are setting x equals to 0, so this is equal to 32y squared, 5. This is 5 equals, 5 over 32y squared. Okay, and let's take the square root of 5 over 32. And this is about positive or negative 0.4. Okay, so I'm going to draw our main graph here, right? And as we add things, I'm just going to do the work for the other values below. But now we have our first one. So at 0.4-ish and positive 4 and negative 4. Connect these all together. This gives our first curve as an ellipse. Okay, in red, we're going to work with 1. Okay, so now we have 1 is equal to 4x squared plus 10y squared minus 64. And so we can cross multiply and divide, I'm just going to make this equal to 1 over 1, which is still 1. So we can do 12x squared plus 6y squared equals 4x squared plus 10y squared minus 64. Let's move things to one side. This is 12 minus 4, which is 8x squared. And this is minus 4y squared is equal to negative 64. Already, I feel like this is going to be a hyperbola, so let's just confirm that. So divided by 64, that's going to leave 8 on our bottom, and this is going to be negative. And this is positive y squared, and 64 divided by 4, 16 at our bottom, equal to 1. So this is a hyperbola. And same thing, we want to find if it opens up or down or left and right. Okay, so let's set x equal to 0. So that gives y squared over 16 equals 1. And already we can see that there are y-intercepts, so this is going to open up and down. Okay, so let's add those values. Right, and it has y-intercepts at 4 and negative 4. None of this is to scale, of course. Okay, so that is our second one. And then our last one, I'm going to do in green. Or did I do the other one green? No, I did that one in blue. Okay, so this is negative 1 over 1. And this is 4x squared plus 10y squared minus 64. This is 12x squared plus 6y squared. This is negative 12x squared minus 6y squared equal to 4x squared plus 10y squared minus 64. Let's move things over to one side. So this is 64 equals 16x squared plus 16y squared. And 16 over 64 is 1 over 4. So then this is 1 is equal to x over 4 plus y squared over 4. This is a circle with radius 4, centered at 0, 0. So then this is going to give us a circle that looks like that. That's supposed to be a circle. All right, and that is the end of this question. So this looks more similar to some topographical maps that we're used to seeing. Okay, so now we're going to talk about partial derivatives of the first order. So partial derivatives is a way of deriving equations that have more than one variable in it. So you're going to have to split them out into however many you have. So in a regular expression, we were only usually working with like deriving just one variable, right? So if you had like x squared plus x cubed minus 3, you could derive that no problem, right? But what do you do if you're given something like this? Right? So this is when you're going to need to separate them into two different kinds of operations. You're going to do it with treating x as a variable first. Well, it doesn't matter which one you do first. And then you're going to treat y as the active variable. So if I were to work with this example, x is a variable and y is just some constant, right? So you can just sub y as like 1, for example, right? So if I were to do just with respect to x, treat x like you would, but since all of this term is just equal to, like, so if we plugged in y as equal to 1, this would just be 1. So that becomes 0. This 3 becomes 0, and this y, which we just considered to be a constant, so for example, we called it 1, that would just be 0, right? So all in all, this only comes out to x squared. And now when we solve with y as our active variable, we're going to treat our x's as constants, right? So x squared, you could make that equal to, you make x equal to 2, any constant, right? Because all constants just turn into 0. You derive y the same way you usually would. This constant is 0 and plus 1, right? So basically just knowing how to separate each one. Now what if you're given, let's do x cubed times squared, and let's solve the partial fractions. Let's do x first, and then y. So you don't have to worry about product rule or anything, because if we start with x, let's just say this is equal, this is just like saying x cubed times 2, right? That means you just bring your, okay, so I'm going to plug this in for 2. It's like saying 2 times 3. And then your x reduces, right? And then if we plug y squared back in for 2, this is just y squared 3x squared, right? So you just keep that as its own variable, as a constant. Don't do anything with it, just pretend it looks like another number. And when we do that for our y, we derive our y variable, and then we just add that coefficient x as if we were treating it as a constant. Okay? So that is one notation we can use, is with whatever you want to derive, just in the kind of low corner. Additionally, we also have these other ones. You'll see both of them just as often, right? But these are some other ways to show partial derivative notations. Okay, so if I were to explain this one through, actually, no, I'm not going to explain it through. I am going to just show you this on screen. Feel free to take a picture and try it on your own, and just kind of solidify your understanding of partial derivatives. So once we do some examples, it will make some more sense, right? But that is how to do partial derivatives in the first order. And partial derivatives in the second order, they could be denoted like this: dx dy, where this is equal to first doing with respect to x, and then doing that with respect to y, right? So that's kind of like a shelled operation. That's one way to define it. There's some other notations that look like this. So you could do x with respect to x, then respect to x again. You can do with respect to y, then y again. And you can do with respect to x, then y, and y, then x. And it's important to note that when you have two different variables, order does not matter. Doesn't matter in this case. So if you derive with respect to x, then y, and then do y, then x, it's still going to give you the same answer, right? So this can be helpful. This is a helpful rule, because you could just start with whatever you find easiest. Okay, so I'm going to take a look at this example here. So we are given, so we have 3 variables. It's equal to xy plus xz plus zy. And we want to find our second order derivative of our partial fraction, it's partial derivatives. Right, so you can write this as dz and dy Okay, and this example wants us to start with our y first. Honestly, it doesn't matter which one you start with, so to kind of do proof of concept, I'll do it both ways to show you. So I'm going to do this one first. So let's start with that. So we're going to keep this outside and inside with respect to y. So this is like saying 2y, and our derivative is just 2, where our 2 is our x. So this becomes x plus, there's nothing here. So we treat, in the case where we have 3 of them, that means we're going to have 2 variables that we're treating as constants. So since we're doing y first as our variable, that means z and x are acting as constants. So in this one, this just be a pure constant, so that's 0, and then plus z. And now we are going to find the partial fraction with our second step. Now using z as our active variable in this equation. So this is just going to be this is going to be equal to, so our x is a constant, so that's 0 plus 1. Right, and that's just equal to 1. So I'm going to do the same thing, and I'm going to do it the other way around. So let's say we start with, what if we start with this first? Right, so what if we start with our z first? Well, this is going to be 0 because x and y are treated as constants. It's going to be x plus y. And then when we do it to our y variable, it's supposed to be y. Now when we do it with our y variable, then this will give us, so we're treating z and x as constants, so this is 0 plus 0, x is a constant, plus 1. We see this gives us 1 both times. So if you come across a question that wants you to solve second order derivatives with 2 different variables, pick whichever one is easiest first. Okay, I'm going to skip this level curve example because I think we're pretty solid on our level curves. Okay, so we're going to find all second order partial derivatives. So when it says all, it wants all the different unique combinations we can have. So we will have 6 combinations. So you have starting with x, ending with x. Right, this is just with 2 variables. It might not be 6. I don't think so. Then you have y and y. You're only going to have 4. And then you have x and y. And y and x. So even though technically these two are the same, we're going to treat them as if they were different just to show you. Okay, so in our first case, let's do with x, then x. So this is, then we start with x here. So this is, this is going to be product rule. So we're going to start by taking our second and not changing it, multiplied by the derivative of our first one. And this is plus our second derivative. So this is like saying 2x to the power of 2x, because we're treating our y as if it were just a constant. Right? And if we move this down, we will get the derivative. So we're going to keep the power the same. And we know the derivative of our exponent comes down. So in this case, our constant is y. So this is y comes down, and this is x, y. Okay, and times x squared. So we're going to simplify this a little bit more. This is 2x plus okay. And now we are going to derive again. So 2x times exy. So this is its own product rule. So we're going to do our last term times the derivative of our first one plus the derivative of our next term times our regular first term. Okay, so this is 2exy plus 2xye to the xy. That's our first one. And then our second one is, so that's x squared and y e xy. We consider this its own term because this is just like saying 2xy, and when we do product rule, it doesn't really have any bearing on it. So same thing, let's do our derivative of our second one. So this y is going to come down again, so this is going to be y squared exy times the derivative of our first one. Times our first one regular, and plus our derivative of our first times just the regular second one. And this is going to give us, okay, so that's x squared y squared e to the yx plus 2xy e to the xy. It's a little messy, but that would be our first one. So let me just check my answer key to make sure I'm on the right track. Okay, and let's do some factoring. So let's take this exy term out. Okay, and that gives 2 plus 2xy. And then that's plus x squared y squared plus 2xy. Let's simplify it even more. So I can take a 2 out of these two terms. That's 1 plus xy. And let's take actually, no, I'm just going to leave it like this. Feel free to simplify it more if you'd like. As an end result, this should give e to the xy. So you can do all the in-between steps. This is x squared plus y squared, x squared y squared plus 4xy plus 2 is our final answer. Okay, so I would like you to try the double y on your own, as well as at least one of these two, right? It is a little time consuming. This one is a little bit more confusing and challenging, but I know you guys can do that. Okay, I'm going to move on to the next couple examples. So this wants us to find numbers for a and b so that it satisfies this equation which deals with our second order partial derivatives. So the first thing I'd like to do is just to find what our wx is on its own. So this is just taking our first order derivative with respect to x. So this is 5 times x to the 4 plus, and this a and y are both going to be treated as our constants. And this is times 3, because that 3 is going to come down from our x, and it's x squared, plus, and this x is only to the power 1, so the x goes away, and that leaves us with that. Okay, and let's do this again. So we're going to do 20x cubed plus 6ay squared times x plus, now this whole thing's going to get treated as a constant, so that's plus 0. Okay, so that is our first set done. Now we're going to find our first partial derivative for y, and we're going to see how this comes together. So this is just 0 plus, so now we're going to put our 2ax cubed, and this is plus 4bx y cubed. And when we do it again, this gives, so that's 0 again. There's no, actually there should be a y value there. Sorry, so this becomes 2ax cubed. And this is plus 12 bx y squared. Okay, so now we're given our equation, so we want to use our value for our wxx. So this is 20x cubed plus 6ay squared x. And we want to make that equal to our double derivative of our wyy. So this is 2ax cubed plus 12bxy. Okay, and now we're going to find some common factors between them. Sorry, this is supposed to be plus. It's equal to 0. So we're going to find some common factors between them. So we can see that we have an x cubed here. So let's separate that out, and this is 20 plus 2a. And we also have x and y. So we're going to take the x and y out. This leaves 6ay plus 12b equal to 0. And now we're going to just take each of the components inside and equate them to 0. So since this only has one variable a, let's start with that. So this is 20 plus 2a equal to 0. Right, because it doesn't matter what this is. As long as whatever this coefficient is multiplying into, it's still going to be 0, right, if we make this equal to 0. So that's 20 minus equals negative 2a, and that is a is equal to negative 10. Okay, and now when we deal with our second one, we can plug our value for a to find b. So this is 6, and our a was sorry, made a mistake. This is y squared, because there's still this y squared here. I forgot to write that down. Okay, sorry. This gets rid of our y term. Okay, so that's 6 times negative 10 plus 12b equals 0. So that's 60 equals 12b. And that means b is equal to 5. Okay, so we solved for our coefficients there, right? And those are the values that we can use that satisfy this equation. Okay, let's do another version of this question. So this is the last part of our lecture. Okay, so let's work with this one now. So now we want to find value k that will satisfy the equation. So let's just do single variabled ones first. So this is sine 8x plus some constant. We don't care about it because this is going to be, so everything in here stays the same. And since 8 is attached to our x and we're working with respect to x first, then we take the derivative of 8x term, which is 8, move that to the front. And this is product rule, so we're going to keep this the same. Okay, and this is plus, so we're keeping our first term the same. And the derivative of our second term is just 0, right? Because there's no x in here, so we consider all of that to be equal to a constant. Okay, so since that's multiplied by 0, then this can just go away. Okay, that's our first one. Second one, so we are going to do with respect to y now. So that means we are going to have that k come out in our sine, and this is, keep whatever is inside the same. Same thing, it's going to be equal to 0 when we do our second part of our product rule. So we are just going to stop there, and then let's do it for z. So this is all just a constant, so that's just going to stay there. And this is multiplied by our derivative of our second term, 17z, and that 17 is going to come out to the front. Okay, so that is our first part. Now let's do our second part. So now we're going to do x again. So this will be 64. Oh, I apologize, I was supposed to change these. This is cos. Sorry, forgot my rules. Okay, so that means this is negative 64 sine 8 plus ky, because we took that 8 out again, right? We're turning our cos back into our sine and adding our negative. And this is going to be the same thing because we have no x terms in it. Okay. Our next one is 4 double y. So this is negative k squared now, because we took that k out again from our y variable. And this is sine 8x plus ky. Our brackets stay the same. So does our cosh term at the end. And we are going to do our z, which is equal to 17. Sorry, this term stays the same. We're going to have that 17 again. 17 times 17. So it's 289, right? Because the 17 comes back out again. 289. Our sine term stays the same because we're treating it as a constant. And we're deriving this again, so that just turns back into cosh. Okay, so those are the 3 parts. All right, now I want to add these all together so they are equal to 0. So let's start with 8x plus ky equal n times cosh 17z. Okay, and this is plus our blue one, so that's minus k squared sine. I'm not done, sorry. And in our purple, we have plus 289 sine 8x plus ky equals 0. So let's simplify this. Let's factor out some parts. So each of these has a cosh 17z term. So let's take that out. Each term also has its sine 8x plus ky. So this is sine 8x plus ky. And now we have 64 minus k squared plus 289. And let's just combine the 64 and 289. So 289 minus 64, that's 225. That's negative k plus 225 equals to 0. So like we did with our previous one, we're going to ignore the terms we factored out and just look at the ones that still remain in our square brackets. So let's look at this and make it equal to 0. It's negative k squared plus 225 is equal to 0. Let's move that k over. K squared. Right, and when we take the square root, this k is equal to plus or negative 15, and that is a beautiful number to end with. Right, so this one was a lot of work, but once you get stronger at your partial derivatives, it will make a lot more sense and it will be really easy to factor out some of these terms. Okay, I'm just going to check my answer to make sure I did it correctly. Yeah, plus or minus 15. So that brings us to the end of this video where we talked about level curves. We also talked about how to find domain and how to use partial derivatives to the first and second order to find values for unknown constants in an equation with multi-variable functions. I hope you learned from this video and I hope you enjoyed, and I will see you in the next video where we'll be delving a little bit more into these applications for these processes. Thanks for watching.